Okay, in this video I'll just make a few comments about section 3.4. So in some sense he doesn't introduce anything really that new. He talks about proofs and using AND statements, which using AND statements we have been using all the time already. You know, we have more than an assumption, you know, we're assuming we're using AND statements. Now, proving an AND statement is also not that difficult or not anything too different of what we have been doing. If you want to prove P and Q, well, basically you have to prove both P and Q, right? So it's not really new, but it might break if you're saying or if you say like if P then Q and R, you assume P and then you prove both. You might need two different proofs, like two proofs in one, okay? So that's basically it. If you have an AND statement that you want to prove, you have to prove each part of the AND. Perhaps, you know, break down in parts. Now, some examples that are usually an AND in disguise are things like equality of sets. So if I want to show A is equal to B, the standard way to show these is to show that A is contained in B and B is contained in A. That's what the sort of thing that you should excuse me, should keep in mind when you're proving equality of sets. Okay? Is breaking in two proofs. Take an arbitrary element of the first, prove that is in the second, and then take an arbitrary element of the second and prove that is in the first. So it's a two-part proof. And you see, you know, some people, you know, will emphasize which part they are doing. You know, I'm going to do this containment here, so he puts a proof in here, and then I'm going to prove this other containment, and I'm going to do another proof in here for the other part. So you break these in two parts. Okay, so this is one statement, one kind of statement that usually is, well, it is an AND statement in some sense, and usually you break in two parts. Prove the first, and then prove the second. Another situation where this happens is if you have an if and only if. Okay, so the AND is already appearing in what, you know, you're saying. So it's an if and only if. Or perhaps it can be phrased as necessary and sufficient. Or another way to say is it's equivalent. Okay? Or this is the same as to say these are logically equivalent or just equivalent. So there's no AND in there, but again, if it is equivalent, it's an if and only if. So there's two parts in here. So if you see an if and only if in your mind, you have two things to do. Show that if P then Q, and if Q then P. Of course, you can use contrapositives in here. So for instance, you could prove if P then Q, and if not P, then not Q. But in either case, you're going to have two parts most of the times. I'll make a few comments about that in a little bit. But most of the times you're going to have two parts. So again, similar to this, you don't do that in a paper. I mean, you never do these sort of things in a paper. You actually just say, let's prove the first, instead of using this shortcut in here, just say, let's prove the first inclusion, namely A is containing B, and you say something similar for the other one. So you don't take these shortcuts in a paper. I mean, you don't see these sort of things in any published paper. But, you know, in the board and even in your homework, you know, it's a shortcut and it shows what you're trying to do, so it's helpful. Here is similar. What you can do is put an arrow in here saying, because this is an if and only if, right? So it's logically equivalent in there. So you can say, I'm going to assume P and prove Q and write a proof in here, and then you write another proof for the other. So here you assume Q and prove P. And you can state, well, we're going to assume not P and prove Q is still the contrapositive, right? Because it's equivalent to the arrow backwards, right? So here, the arrow goes backwards because, of course, if you want to, you're doing this. If Q then P. So again, you see that a lot on the board. Again, you wouldn't write it on paper, but in your homework on the board, I'll use these sort of things. Okay? Now, so lots of times, these two kinds of proofs, equality of sets and equivalency, or if and only ifs, are broken into parts. On the other hand, we've done a few equality of sets, and we didn't break down into parts. So there's one way that you can do both of these without breaking into parts. You do it in one single shot. You can't always do that, or it's not always easy to do that. Okay? So sometimes it is actually easier to break into parts. But sometimes what you can do is the following. If I want to show the equality of these two sets, well, what you can do is to start with an arbitrary element of the first and connect with an if and only if, some other property here, and perhaps a few more if and only ifs, some other property. And at some point, connecting every single statement to another by if and only ifs, you get in the end that x is in B. Because these are all if and only ifs, we have both at the same time, because we're saying that if something is in A, if and only if something is in B. And that's also the equality of two sets. So we're like using this if and only if here in the equality, right? So that's the same. You can rephrase these as x is in A, if and only if x is in B. So x in A implies x is in B would be A containing B, and the arrow backwards would be the other containment. Okay? So this would be one way where we could do things like this. Now, similar in here. One way that you could do this is you start with P and manipulate it, but always connecting with if and only ifs. If you can always use if and only ifs. Here's something, maybe some intermediate step, another intermediate step, and eventually, with connecting every pair of statements by if and only if you can get to Q, then you prove this statement here in one single shot. But you have to be careful. You have to be able to guarantee that whatever comes in here, so you have a P prime in here, is it really if and only if? Or can I just say if P then P prime, but not if P prime then P? So sometimes these steps they're not easy to come up with if and only ifs. Okay? But one case that is always if and only if is that if you're using definition by definition. So definitions always go both ways. So if you're connecting things by definition, then you can do it in one step. And that's how we've done in the past equality of sets in single steps. It's because everything was connected by definition. Okay? So these are my remarks for this section, and then we're going to start doing some problems.